We're now going to look at AS Chemistry Paper 2. This is Specimen Set 2. So we have a curve here, and we'll ask to draw on the same axis a curve for sample 1 at a lower temperature. So the area underneath the curve has stayed the same because the sample hasn't changed, the number of particles are the same. It's going to go through 0, 0 because no particles have 0 energy. At a lower temperature, then the peak is going to be to the left, because the majority of the particles will have a lower energy at a lower temperature. So the peak is going to be somewhere here to the left of this one. It's going to end up coming underneath this curve. It's never going to touch the x-axis because there's always a number of particles with a very high energy, and it's going to go underneath this other curve. So it's going to go into that little space here. The peak height is going to be higher than the other peak because the number of particles hasn't changed and the area underneath the curve hasn't changed because it's the same sample. So let's look at it again. 0, 0, no particles have 0 energy. The peak is to the left because the majority of the particles have a lower energy because it's a lower temperature. So most particles here have a lower energy than they do on the other sample. And it always goes underneath the other curve because there's fewer particles with a higher energy, although there are some, hence it being above the x-axis. Explain the effect of lowering the temperature would have on the rate of reaction. So lowering the temperature gives particles less energy. More importantly, fewer particles have the activation energy. That's the important thing. Activation energy is the minimum amount of energy that particles need to have for a reaction to occur. So fewer particles have the activation energy. That's important when we're considering temperature, and so there are fewer successful collisions. You've always got to use the word successful collisions. Let's have a look at what's happened here. So deduce the change that was made. Well, this time the area underneath the curve has changed, and the area underneath the curve for sample 2 here, this area, is less than all of this area. So in actual fact, sample 2 has got less gas in it than sample 1. There's less gas in it because the number of particles represented by the area underneath the curve has gone down. So the change is that there's less gas in sample 2 than there is in sample 1. The explanation on the rate of reaction, well, explain the effect on the rate of reaction. The rate of reaction will be lower, but the reason is, for the explanation, the reason is that the particles are further apart. There's no indication here that there's anything to do with temperature. So the reason is because there's fewer particles in this sample and the particles are further apart. Again, you've got to mention successful collisions. So in sample 2 the particles are further apart, so there are fewer successful collisions. It tells you a little bit about avgas. It tells you it consists of hydrocarbons, so hydrocarbons contain hydrogen and carbon only, no other elements, including a high proportion of hexane, can exist as several isomers. Okay, draw the skeletal formula. So remember, a skeletal formula is just a series of lines, and at each corner or at each end there's a carbon. You don't draw the hydrogens on there, and you do it in a zigzag pattern. Draw the skeletal formula of 2 branched, so the important word is branched. Branched isomers of hexane. So hexane 6 carbons in a line. So you've got to have a branch. So if you have a branch, then you've got to reduce the number of carbons in the main chain. So there could be 5 in the line with 1 branch. So you could have 5 in the line with a branch. The branch can't be at number 1 or number 5, otherwise there'd be 6 in a line. It'd be hexane. So it could be, the branch could be at number 2, or it could be number 3. So you could have 2-methyl pentane, or you could have 3-methyl pentane. So 2-methyl pentane would look a little bit like the top one. 1, 2, 3, 4, 5. Notice we've got, you can put dots at these points if you want to, but we've got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and the methyl group there. So that's a carbon there is a methyl group at number 1, 2. So 2-methyl pentane. And this one is 1, 2, 3-methyl pentane. This methyl group going up could also come down, and this one going down could go up. It doesn't really matter which way it is, and a zigzag is the way to show that there's a carbon on each corner. Incidentally, you could have 4 in a line. There's no reason why you can't have 4 in a line, but with it being hexane, 6 carbons, you need 2 branches this time. So I've got 1, 2, 3, 4 carbons there with a branch, a carbon there and a carbon there. So I've got dimethyl butane now, so 4 in a line is butane, dimethyl. I better say where these are. They're at carbons number 2 and number 3, so I've got 2,3 dimethyl butane, and this one, in actual fact, 1, 2, 3, 4, I've got dimethyl butane again, 1, 2, 3, 4. If I start labeling from this end here, so if this is carbon number 1, that ends up as carbon number 2, rather than the other way around. That'd be 1, 2, 3. So at carbon number 2 here, I've got 2,2-dimethyl butane on this one. State the type of isomerism. Well, it's a kind of structural isomerism. Remember, structural isomerism is where the molecular formula, the number of carbons and hydrogens, stay the same, but the structural formula changes. So the molecular formula stays the same, but the structural formula changes, and so the name will change. But there's 3 kinds. So the first kind is positional. The first kind is chain, really. The second kind is positional, and the third kind is functional group. So chain is where you change the length of the chain, so we've clearly done that, so the answer is chain. The other one is positional, where you've just changed the position. Well, you could say here, I've changed the position of this to this one. So these two are positional isomers of each other, but the question is asking, how are these isomers related to hexane? So hexane's got 6 in a line, here's got 5 in a line or 4 in a line, so the branch means that there's fewer carbons in a line, so the chain isomers. Although these two are actually 2-methylpentane and 3-methylpentane are actually positional isomers of each other, where the position of the functional group, the methyl group, is changed, and then you can have a functional group change where, I don't know, where the ending changes, where an ane becomes an ene, or an aldehyde, an al becomes an O, and a ketone, or something like that. Chain isomerism, because hexane has been changed to give 5 in a line or 4 in a line with branches. Change the length of the carbon chain. But there's 3 different kinds of structural isomer, chain, positional and functional isomer. So you probably could have got away with structural isomerism as well. Safety signs on the fuselage of a helicopter state the air inlets to the engine need to be cleaned out regularly. Write an equation for the combustion. So combustion is a reaction with oxygen, burning, a reaction with oxygen of hexane. So you have to know what hexane is. It's C6, and then you double the number of carbons and add 2. So 6 times 2 is 12, add 2 is 14. So it's C6H14. That would happen in the helicopter if the inlets were partially blocked. In other words, there's not enough oxygen. There's incomplete combustion. Complete combustion makes carbon dioxide and water. Incomplete combustion makes carbon monoxide and water. It can also make carbon and water as well, a black solid carbon. So I think you need C6H14, then you need some oxygen to make carbon monoxide, partially blocked, incomplete combustion, carbon monoxide and water, and then you can balance it. The easiest way to do it, first of all, is realize you've got 6 C's, so you can need 6 C's here, 6 COs. You've got 14 H's, so you can need 7 H2O's here, because 7 times 2 is 14. Then you add up the number of oxygens. 6 times 1 is 6, 7 times 1 is 7, 6 adds 7 is 13, so you got a number multiplied by 2 that equals 13, that's 6.5. You could incidentally have made carbon here and balanced it instead of carbon monoxide probably as well, but carbon monoxide is usually the gas that's made if something happens, if there's not enough oxygen around to provide complete combustion, and in this case it's called incomplete combustion to make carbon monoxide, an insufficient supply of oxygen, a non-plentiful supply of oxygen. Suggest how the partial blockage might affect the performance of the helicopter engine. Well, it's going to become less efficient. So there's probably various different ways that you can answer this question. Less efficient, needs more fuel to produce the same efficiency, something like that. Less energy given out by the fuel, energy is less powerful or less efficient, yes. It needs to burn more fuel to get the same energy, increased cost due to need more fuel. I think the best answer is energy is less efficient. That's probably the most popular answer. Draw the displayed formula of 1,1,2 trichloro 1,2,2 trifluoroethane. So the first thing to note, ethane has got 2 carbons, so each carbon will have 3 bonds. There's 6 bonds coming off, and there's trichloro 3 Cl's, trifluoro 3 F's on ethane. So if there's 2 carbons each with 3 bonds, 6 bonds in total apart from the bond between them, so it's going to look like this. There's going to be 3 chlorines, 3 Cl's, 3 F's, and 1, 1, 2 for the Cl's. If this is carbon number 1, 1, 1, 2. So 2 at number 1 and 1 at number 2, and vice versa. A fluoro, 1 fluoro at number 1, carbon number 1, there's the fluoro, and 2 fluoros then at number 2. So 1, 1, 2, 1, 1, 2, carbon number 1, carbon number 1, carbon number 2, trichloro, 3 chloros, 3 Cl's, 1, 2, 2, an F at carbon number 1, and 2 F's, an F and an F at carbon number 2, trifluoro, 3 F's on an ethane backbone and ethane chain. Write 3 equations to show how 1, 1, 2 trichloro, 1, 2, 2 trifluoroethane, so this chemical was banned for use as a refrigerant, how it reacts with the ozone layer. So I'm just going to show you this so I can talk you through it. So what you've got is, you've got CCl2F, CCl2F, and then you've got CF2Cl, CF2Cl. Now what actually happens is, during the initiation reaction, so to start off with then, a Cl dot is always made, a chlorine radical. Now the chlorine radical can either be, the Cl can come from here, or here, or here. It doesn't really matter. And you're going to make something. Let's assume it comes from here, so this is gone. So I'll have CCl2F, CCl2F, and I'll have CF2, CF2, and then this Cl is the one that's gone. The 2 electrons in there, one's gone onto the Cl and one has gone onto the C. They've split, so one's gone one way and one's gone the other way when that bond has been broken by UV light. So I should really put UV light above the arrow here to show that it's UV light which is providing the energy for that bond to break and an unpaired electron to go onto the Cl and an unpaired electron to go onto that C. Now I've not drawn, you can see the unpaired electron there on the Cl, and there isn't one on this C. It's this C that should have the dot, because it's this C that's lost the Cl. This C here has only got F2, it's got these 2 F's remaining. It's short of a bond, it's not got enough bonds, and so that electron from the bond has gone on to the C when that bond's broken, so that should have a dot on it here. If you'd done it the other way around, if you'd lost a C from here, that would have been okay. You could have C dot, C dot, F, Cl, CF2, Cl. That would have been okay as well. The next stage is that this chlorine radical that's very reactive reacts with some of the ozone. You need to know that ozone's O3. And O3, there's 2 kinds of oxygen, O3 ozone and normal oxygen O2. So the only thing that this can turn into is O2, and then you can work out what's left. Well, I've not used a Cl. I've not used one of the O's now because there's 3 there and there's only 2 here, so there must be an O, and the dot's got to continue. The dot can be anywhere really. It doesn't really matter where the dot is. This is going to react again and reacts with more O3. What's the only thing that O3 can turn into? O2, and I've got 4 O's here, so if I put 2 in front of the O2 it balances the O2, and what I've got left that I've not used a Cl, there it is, and I've not used the dot, and that goes onto the Cl and replenishes the Cl. That means that this is a chain reaction. That Cl that's made keeps being remade. It's a catalyst. Which of the following would cause least environmental damage? So the one without any Cl's in. So Cl's can form chlorine radicals. if you expose them to UV light. That's got CLs, that hasn't got any CLs, that's got CLs, so B is going to be the one that causes least environmental damage, with no chlorines, no CLs, and it gives the name of compound B. So it's CF3CH2F, so it's a kind of ethane because there's 2 CLs. It's got 4 Fs, so it's not fluoro, it's not difluoro, it's not trifluoro, it's tetrafluoro, and I better say where the 4 Fs are. There's 3 of them, 1, 1, 1, 3 of them at carbon number 1 and 1 at carbon number 2. So it's 1, 1, 1, 2 tetrafluoroethane. The boiling point of iodomethane is higher than that of fluoromethane. Explain why, even though the electronegativity of iodine is less than that of fluorine. Well, first of all, iodine is further down group 7. It's low down in group 7, fluorine's at the top. So iodine is a bigger atom. Bigger atom, more electrons, more attraction to the nucleus of a neighbouring molecule, stronger van der Waals forces. So the iodine is a bigger atom than the F, so CH3I will have more van der Waals forces than CH3F. On the other hand, the electronegativity of iodine is less than fluorine, so the CF bond here is going to be more polar. This is going to have a delta plus on the carbon and a delta minus on the F, because the F is more electronegative. So that's going to have a more polar bond between the C and the F than the C to the I, because the I is less electronegative, and so going to have a smaller delta minus. So this is going to have more polar bonds, and between the molecules, that's dipole-dipole attractions. So this will have stronger dipole-dipole attractions. So this will have stronger van der Waals forces, this will have stronger dipole-dipole attractions. And then why CH3 molecules have a higher boiling point, it must be that the van der Waals forces provide a greater attraction, are stronger than the dipole to dipole attractions. Question 4. Name the reagents that the student could use to identify that the sample was pent-1-ene. So you're looking for presence of a double bond, so you could use bromine or bromine water. Observation is that it goes from orange to colourless. Name the reagent used to identify the sample was pentanoic acid. So the easiest way of doing this is adding something like sodium carbonate that's going to form bubbles. I suppose you could add a universal indicator which would go orange, but sodium carbonate producing bubbles, or effervescence, but bubbles is easier to write down than spell, so bubbles will get you the mark, is the best answer. Name the reagent. Sample was pentanal, so an aldehyde, so you're looking for Tollens reagent. Now at AS you'll get away with Tollens reagent. At A2 you need to put warm Tollens reagent, and the observation is a silver mirror. Alternatively, you could use failing solution that would give a brick red precipitate. So at AS, Tollens reagent will get you the mark. Warm Tollens reagent is needed. The word warm, the condition is needed at A2, gives a silver mirror. As I say, failing solution given a brick red precipitate would also suffice. The student deduced that the spectrum was that of pentanal. So pentanal has got a carbon to oxygen bond in it at the end of a chain. Justify this deduction and suggest why the spectrum cannot be that of pentan-1-ol, pentanoic acid and pent-1-ene. So for 4 marks, so I think first of all you need to say what's in this that identifies the carbon to oxygen double bond, and what's not in this that should be present if it were pentan-1-ol, pentanoic acid and pent-1-ene, to show that it's not these 3. So pentanal has got a carbon to oxygen double bond, so you need to look up in your data table what absorption that's got. It's going to turn out to be this one here. And then you need to work out what an OH is in an alcohol, where that would appear. It's presumably not present. Pentanoic acid, so an OH in an acid, where that should be, and presumably that's not present. And a carbon to oxygen double bond in the ene won't be present either. So absorption at 1680 to 1750. By the way, you need to quote these numbers from the data book. If you don't quote the numbers from the data book and write them down, it's only a matter of copying after all. If you don't copy these numbers down, then you don't get the mark. So there is an absorption at 1680. There it is. It's absorbing due to the presence of a carbon to oxygen double bond in the pentanal, and there's no absorption at 1620 to 1680. There's nothing there. 1620, so we'll be about here. There's nothing here that would be caused by a carbon to carbon double bond, so it's not pent 1-ene. No absorption 3230 to 3350, which would be the OH in an alcohol, so it's not pentan 1-ol. An OH in alcohol, by the way, gives a very, very broad absorption. It's not a sharp absorption like that, it's a very, very broad absorption, and it's not there at 3220, 3230 to 3350. It's just not here, that broad absorption for an alcohol, and there's no absorption at 2500 to 3000, which would show the presence of the acid, so it can't be pentanoic acid because there's nothing here in this region here, 2500 to 3000. They're not really significant absorptions. I think those are due to carbon to hydrogen or carbon to carbon bonds. 2-methylbutene reacts with concentrated sulfuric acid to form two different products. Outline a mechanism for this reaction. Show the formation of the major product. It's going to be difficult to explain this without showing it, so I'm going to do spoilers. So let's have a look. 2-methylbutene reacts with concentrated sulfuric acid. Butene, 2-methylbutene, 1 carbon, 2 carbon, 3 carbons, 4 carbons. So it's got 4 in a line. It's got a methyl group at carbon number 2, so this is carbon number 1, this is carbon number 2, and there's the methyl group, and it's bute, 4 carbons in a line with a 2-ene, a carbon to carbon double bond at carbon number 2, 1, 2, and there's the double bond. Sulfuric acid, well, in the mark scheme they've written it out like this. I sometimes refer it as HOSOH, so an S with an O and an H and no and an H, and two S to O double bonds, but you could write it out like this as well if you wanted to. So I tend to show it again as HOSOH, and then the S having two oxygens with S to oxygen having double bonds. But I don't suppose there's anything wrong with writing it out like this. An area of lots of electrons in the carbon to carbon double bond, so the electrons come from here, and the electrons in this second bond here join to the H. The reason they go to the H and they bond to the H is because this is a polar bond, and the O is electronegative with a slight minus, a delta minus. This has got a slight delta plus. They've not drawn this on here. It would be better if they did, with the slight delta plus on this and a slight delta minus on here, but they're letting you get away without showing that this is a polar bond. And if the H is going to bond to one of these two carbons, then this bond needs to break and the electrons go onto the oxygen. So the question is now, where does this plus go? So, or rather, where does the H go? In the major product, the H joins the carbon, bonds the carbon that's got the most H's. So this carbon here, or this carbon here, wherever you want to say, this carbon here has got no H's joined to it. It's joined to a carbon, and it's joined to a carbon. It's joined to a carbon, it's joined to a carbon. It's got no H's joined to it, bonded to it, whereas this C here has got one H bonded to it. So the H bonds to this C, the carbon that's already got the most number of H's bonded to it. This hasn't got any H's, this has got one H. So it bonds to this carbon here. It doesn't really explain why, but at least means that you've got the H bonded to the correct carbon. And there's the H. The H there is bonded here onto this carbon. Now this carbon has now, since the H is bonded to the other carbon, hasn't got enough bonds. That means it's got a plus because it's lost a bond. Electrons are in bond, it's lost electrons, it lost minuses, it's become plus. and the electrons here have moved on to the oxygen. That's become minus. So this oxygen now is going to bond to this carbon. Remember, the arrow, however, doesn't come from the minus charge. The arrow comes from the lone pair of electrons. The pair of electrons in this bond have been deposited onto the O, and there they are, and the arrow comes from the O onto this C+, the carbon that's not got enough bonds and has got a plus. Then the minus and the plus cancel each other out, so this loses the minus and this gains the minus, the electrons that are moving, and it joins on in this fashion. So draw the structure of the minor product. Well, the minor product is where the H doesn't join the carbon that's got most hydrogens. So it doesn't join this carbon with most hydrogens, it joins to the carbon with the least hydrogens. That's very unlikely to happen, hence it being a minor product. It doesn't really happen very much, just a little tiny bit happens. So the H joins to this carbon here, and the OSO3H joins to this carbon here. In other words, these two are swapped over. The H is joined onto here, it would leave a plus here, and this would attack the plus and join onto here. These two are swapped the other way around. Why do these two products formed in different amounts? Well, let's have a look at this. A C with a plus is called a carbocation. Now, if you count the number of carbons off that C+, it will tell you whether it's primary, secondary or tertiary. So the C+, the carbocation, if it's got one carbon bonded to it, it's primary, two carbons bonded to it, it's tertiary, two carbons bonded to it, it's secondary, three carbons bonded to it, it's tertiary. So this is a tertiary carbocation. So tertiary carbocations are the most stable forms of carbocations. Next most stable are secondary, and the least stable are primary. So the fact that this has formed a tertiary carbocation with three carbons bonded to the C+ makes this very stable and makes this the major product, the reaction that's most likely to go ahead. If something's stable, then it's more likely to go ahead. If the H bonded to this H and this carbon here had the plus, if this carbon had the plus instead, as is the case in the minor product, this C had the plus, then this C would have only two carbons bonded to it. So your answer is that this tertiary carbocation is more stable than the secondary carbocation that would be formed in the minor product. There may be an extension mark at this point. It isn't in this question. There might be an extension mark, say 3 marks. So why does this actually happen? Why is the tertiary carbocation more stable? And the answer is that a tertiary carbocation has methyl groups around it, or tends to have methyl groups around it, which repel electrons. The electrons reduce the size of the C+, by the way, and make the C+, the carbocation, more stable. But your answer is, if it said, why is a tertiary carbocation more stable than the secondary carbocation, or why is a secondary carbocation more stable than a primary carbocation, it's because the methyl groups surrounding the tertiary carbocation repel electrons. Question 6 here, it looks as if we've got a fermentation mixture, we've got some yeast, we've got some sugars in the forms of fruit and vegetables. In the absence of air, it produces ethanol. So we've got an ethanol and water mixture. The absence of air is important, otherwise the ethanol would oxidize in the oxygen and turn into ethanol, and then may further oxidize again and turn into ethanoic acid. But in the absence of oxygen or air, then we're just going to produce ethanol and water. We've got ethanol and water in the mixture here. We need to say how this apparatus is going to allow us to separate the ethanol and water and name these pieces of apparatus. Well, we've got a fractionating column, which is A, we've got a thermometer, which is B, and we've got a condenser with some cool water going through it, which is C. Quite why we need a fractionating column A, I'm not sure. Usually use a fractionating column to separate liquids when you've got a large number of liquids with boiling points that are very similar to each other. We've only got 2 liquids, ethanol and water, and their boiling points are quite a long way apart. Ethanol boils at 79 degrees C, water boils at 100 degrees C. So quite why we need fractional distillation with a fractionating column, I'm not sure. We could get away without having a fractionating column, and we could just use simple distillation if we wanted to. However, we've been given a fractionating column, so we'll go with that. So what do we do first of all? Well, the first step will be presumably to turn the water on in the condenser C, then heat up the flask with a Bunsen burner. The ethanol and water will start to evaporate and will be separated in the fractionating column when the water condenses back down and drops back into the flask. The ethanol gas will then pass through into the condenser C, where it will be condensed and cooled back down into ethanol liquid and collected in the flask. And the purpose of B is to ensure that the temperature doesn't rise above 79 degrees C, or the boiling point of the ethanol. Otherwise, you won't just get ethanol condensing into the flask, you'll also get some water condensing into the flask as well. So turn on the water, heat up the flask with a Bunsen burner, cause the water and ethanol to turn to a gas. The gases pass up the fractionating column A, water and ethanol are separated in A, water condenses back into the flask. Observe the temperature, keep the temperature below the boiling point of ethanol at or below the boiling point of ethanol, and therefore only ethanol gas passes into the condenser. The condenser will cool the ethanol gas and condense into a liquid. Let's have a look at the next stage of the question then. Now this is a difficult question because we've been given density, so we've got density which is mass over volume, but we've not got the mass. So we've got the density of ethanol, mass over volume, and we've got the density of water which equals the mass over volume of the water, but we've not been given the mass of the ethanol, and we've not been given the mass of the water, and we've not been given the volume of the ethanol, and we've not been given the volume of the water. What we're trying to find out, you should assume that the volume of the sample is equal to the sum of the volumes of the water and the ethanol. Use this data to calculate the mass. So we want the mass of ethanol in the sample collected. So what I'm going to do is I'm going to do spoilers first of all. I'm going to show you how this can be worked out. First of all, you've got to give the mass of ethanol a letter M, because I've not got a true value for the mass of ethanol, and that's what we're trying to work out. So we're trying to work out the mass of the ethanol. I'm just going to give it the letter M, and from that point, so the mass of the water is the mass of the sample take away M, because if M is the mass of the ethanol and the mass of the sample is 16, there's only ethanol and water in there, 16, which is the total mass of the sample, take away M, the mass of the ethanol, must be the mass of the water. So now, if I know density is mass over volume, I've got the masses of the ethanol and the water, albeit with the letter M in there. I know the densities of each of them. I can say that volume is mass over density, because I've got the masses and the densities. I can work out the volume of each. The volume of the ethanol is the mass of the ethanol, which is M, divided by its density, 0.79. The volume of the water is its mass, 16 take away M, divided by 1, which is its density. Now then, the volume of the sample is 20. And that's got to equal the volume of the ethanol plus the volume of water. So 20, the volume of the sample, is the volume of the ethanol, which we've just worked out, M divided by 0.79, added to the volume of the water, which is 16 take away M divided by 1. Now, anything divided by 1 is itself. So let's simplify that. 20 equals M divided by 0.79, add 16 take away M, so I can forget the divide by 1. Now I don't like divide by 0.79, so I'm going to multiply everything through by 0.79. 20 multiplied by 0.79 is 15.8. M divided by 0.79 multiplied by 0.79 cancels out the 0.79, that just equals M. 16 multiplied by 0.79 is 12.64, and M multiplied by 0.79 is 0.79 M. Take away M, take away 0.79 M. Now I'm going to rearrange it. I'm going to take the 12.64 across to the other side of the equal sign. So plus plus 12.64 becomes minus 12.64, and that then leaves on the other side m take away 0.79m. 1m take away 0.79m is 0.21m. 15.8 take away 12.64 is 0.21m. I can solve m now. These two numbers subtract from each other are 3.16 equals 0.12m. Divide by 0.12m on this side, divide by 0.12m throughout rather. 3.16 divided by 0.21 equals 15 grams. So my mass of ethanol is 15 grams, and that's what I wanted to find out. For question 7, we've been given a graph. From the graph we've got a temperature change, and then we've made a mixture or carried out the reaction at time 4. That's why we don't have a reading at time 4. So we've got some readings up to time 3 minutes. At time 4 minutes we don't have a reading, and then we've got readings at minutes 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So the reaction's carried out at minute 4. That's why we don't have a reading at minute 4. We need to measure the temperature change when we do that, carry out that reaction, when it first reacts at time 4. So what we need to do is we need to extrapolate this line forward. That means take it forward beyond that point to time 4 minutes, when the reaction's happening. So you draw a line through those 3 points. I'll probably ignore that one. That one seems to be an anomaly. Your line of best fit is through those 3 points, and it'll hit the line there at temperature 23. So the initial temperature at time 4 minutes, is 23. There. Then it goes up and comes back down here. The reason it doesn't shoot up the temperature straight to the top is because there's a little bit of a delay on the actual thermometer warming up and taking these readings. So what's actually happened is, if you extrapolate this line backwards here, this line of best fit, ignore it where it's coming up slowly, take this line and extrapolate that back to line 4, time 4, it probably hits the time 4 at about that point there, temperature 40. So this line extrapolated comes to 23 degrees Celsius at time 4, and this line extrapolated back hits line 4, time 4, at about 40 degrees C. And so if you draw those two extrapolations back, a line back there and hit that at 40, a line forward there to hit at 23, you'll find that the temperature change, 40 take away 23, is 17. The student used 240 milligrams of magnesium and 10 centimeters cubed of trichloroethanoic acid. Use these data information to calculate the enthalpy change. Now, I've been given a specific heat capacity. The only reason that I've been given a specific heat capacity is to use Q equals minus MC delta T. Q is the heat change, the enthalpy change, sometimes known as delta H. So if I do that then now, two extrapolations give a temperature change at the 4th minute of 17 degrees C. Q equals MC delta T. There should be a minus in front of that really. We can add the minus at the end. The mass is 10 centimeters cubed of aqueous. Aqueous means it's mainly water. So you should know that water has 10 centimeters cubed is the same as 10 grams. 1 centimeter cubed is 1 gram. It's got a density of 1. So 10 centimeters cubed is 10 grams. The mass of the solution, you look at the mass of the water, the liquid, not the mass of the magnesium, the mass of the liquid, the water that you're heating up, that's getting heated up in the reaction, is 10 grams. C is your specific heat capacity, which is 4.18. That's why we know, being given a specific heat capacity, that we're using this equation. Multiplied by temperature change, delta T is 17, and it comes out as 710.6 joules. Okay, now that's going to be exothermic, because we know that the reaction is getting hotter, and that's why there'll be a minus in front of it eventually in a minute. Moles of magnesium. So to do moles of magnesium, you take the moles is mass divided by the MR. So milligrams needs to be in grams. So moles is mass in grams divided by the MR. Turn milligrams into grams. Milligrams is smaller than grams, so to turn a small number of units into a larger number of units, you divide by 1,000. So 240 divided by 1,000 is 0.24. That's the number of grams of magnesium. And I've got its MR as 24.3, so my moles of magnesium is 0.00988 moles. So in other words, 710 joules of energy is given out when we react 0.00988 moles. I need to work out how many joules of energy or kilojoules of energy are going to be given out when we use 1 mole. Well, this small amount, less than 1 mole, gives this, so we're looking for a larger number. So what you do is you take the 710.6 and you divide by this, and it'll give you a larger number. So 71923.06 joules for every mole of magnesium that are reacted now. So we now know the number of joules that would be given out when we react 1 mole of magnesium. We make it minus, we divide by 1,000 because joules into a larger unit, kilojoules. Joules into kilojoules you divide by 1,000, so it turns out as 71.92307. It's a minus number because it's exothermic, and it needs to be to 2 significant figures because some of my other values, such as 10 or 17 rather, so my 17 here is to 2 significant figures, so we'll take it to 2 significant figures, minus 72 kilojoules per mole. Let's look at this reaction to make methanol from carbon monoxide and hydrogen. 1 mole of carbon monoxide makes 1 mole of ethanol. 2 moles of hydrogen are needed to make 1 mole of methanol. So it's a reversible reaction, so it can go in forward and backward directions. At the start of the reaction, I've got 0.73 moles of carbon monoxide, I've got 1.25 moles of hydrogen, and I won't have any methanol because none is made yet, the reaction hasn't started. At equilibrium, so that's a point where the forward and backward reactions are going at the same speed or the same rate, and the concentrations of reactants and the concentrations of products are no longer changing at equilibrium, sometimes called dynamic equilibrium. At that point I've made 0.43 moles of methanol. When I make 0.43 moles of methanol, because 1 mole of carbon monoxide makes 1 mole of methanol, if I make 0.43 moles of methanol, I must need 0.43 moles of carbon monoxide to make that 0.43 moles of methanol. So the amount of carbon monoxide that I've now got is what I had initially, 0.73, take away 0.43. 0.30. If you look here, everything here is to 2 significant figures, so I've put these to 2 significant figures as well. 0.30. Now then, the problem is when I make 0.43 moles of methanol, I need, for every 1 mole of methanol, I need 2 moles of hydrogen. So to make 0.43 moles of methanol, I must use up 0.86 moles of hydrogen. I started off with 1.25, take away 0.86 equals 0.39, again to 2 significant figures. Write an expression for the Kc, so that's the concentration of methanol divided by the concentration of carbon monoxide divided by the concentration of hydrogen. Concentration of hydrogen needs raising to the power 2, it needs squaring for the equilibrium constant because there's a 2 in front of the hydrogen, so that's your equilibrium constant expression. In another experiment, the equilibrium mixture contained, so I've got the moles of each of the 3 and I've got the volume. Why would I be given the moles of each of the 3, the carbon monoxide, the hydrogen, the methanol and the volume? The only reason I'd be given moles and volume is to work out concentration. So the concentration, well, concentration is moles, and I've got the moles, but it's divided by volume in decimeter cubed. Centimeter cubed into decimeter cubed, a small unit, centimeter cubed, into decimeter cubed, I'm going to divide by 1,000. So 9.4 times 10 to the power of 3 centimeter cubed divided by 1,000 is 9.4 decimeter cubed. And then if I divide each of these molar amounts, moles, by 9.4, I'll get the concentration of each of them. So the concentration of methanol 0.029, concentration of carbon monoxide 0.0481, concentration of hydrogen 0.1128. So I'm dividing by 9.4 the volume in decimeter cube. They're all in the same flask, so the volume is the same, 9.4. I put these numbers into kc and it comes out as a number 4.75 times 10 to the power of 3. What are the units then? Well, let's have a look at the units here. So units of concentration are moles divided by decimeter cubed. Moles divided by decimeter cubed. I've got one concentration on the top and I've got 1, 2, 3 concentrations, because this concentration is squared, 3 concentrations on the bottom. So if I put those into my units, moles divided by decimeter cubed, moles divided by volume in decimeter cubed, 1 on the top, 1, 2, 3 on the bottom. 2 of those, top and bottom, 1 at the top, 1 at the bottom, cancel to leave just nothing on the top, or rather a 1 on the top, divided by mole divided by decimeter cube, mole divided by decimeter cube. These two are still on the bottom. What's another way of writing this? Well, mole divided by decimeter cubed, another way of writing that is mole dm to the minus 3. The minus means you've divided by the decimeter cubed. I've got another one here, mole dm to the minus 3. How do I simplify that? Well, I've got a mole and a mole, which is a mole squared, and I've got a dm minus 3, dm minus 3. I add these two numbers together to get a dm minus 6. If it's on the bottom and I want it to be on the top, I change the 2 into a minus 2, and I change the minus 6 into a plus 6, so I reverse the signs, positive to become negative and negative to become positive if I want this on the top rather than the bottom. The total pressure in the flask was 482.9 kilopascals. I've been given a gas constant and I want to work out temperature. The only reason I'd be given a gas constant if I wanted to use this equation. It's the only equation I know with a gas constant in it. PV equals nRT. So PV equals nRT. Pressure. Pressure here is in kilopascals. I want it in pascals. To turn a large unit into a smaller unit, I divide by multiply by 1,000. So 482.9 kilopascals into a smaller unit of pascals and multiply by 1,000. So the pressure is 482,900 once I've multiplied it by 1,000 to get into pascals. So pressure's in pascals. One of my bigger problems is now that I've got to get volume. So what's the volume? Well, the volume of the flask, because the flask hasn't changed, is 9.4 decimeter cubed. In this equation here, my volume needs to be in meters cubed. So to get decimeter cubed 9.4 into meters cubed, decimeter cubed into a larger unit value of meter cubed, I've got to divide by 1,000. So it's 9.4 divided by 1,000. So that becomes 0.0094 meters cubed. So now I've got the pressure, I've got the volume. N is the number of moles. Well, the number of moles in the flask is the number of moles of all of the gases added together. So the number of moles in the gases in the flask is 0.452, 0.106, 0.273. That's the number of moles of gas that I have in the flask, and that equals 0.831. So I've now got P, I've got V, I've got N, I've got R, which is 8.31, and if I put all of that in, I end up with this equation here. T I don't know, that's what I'm trying to find, so I'll multiply these numbers out first. It's probably easier to do that first on your calculator, and then temperature is 4539.26 divided by 6.906, which is 657.3. Now temperature is in Kelvin, and it asks for it in degrees C. To get the final mark then, you need to convert Kelvin to degrees C. You subtract 273, you take 273 away from this value. So if you turn in degrees C into Kelvin, you add 273, Kelvin into degrees C, you subtract 273, and so the answer comes out as 384.3. If you look at all of the numbers here, well, 8.31 certainly is to 3 significant figures, so is 9.40 for the decimeter cube. So my lowest accuracy value is to 3 significant figures. That's to 4, so it's best if I turn it to 384 and get it to 3 significant figures. Which of the following mechanism reactions does not occur in bromoethane? Let's have a look. Let's eliminate some. Let's get rid of some. Radical substitution. So methane can react with a Cl dot radical, a chlorine radical. So bromoethane could do the same thing. So free radical substitution could occur with bromoethane with a chlorine radical, a Cl dot. Yes, that's true. Now bromoethane, we've done back in early AS, can react with potassium hydroxide or sodium hydroxide. If the potassium hydroxide or the sodium hydroxide is in cold water, then you get nucleophilic substitution where the OH replaces the Br and it would make ethanol, and Br minus would come off. If you end up with warm ethanol, so if you put it in warm ethanol, what actually happens is you get an elimination reaction then, where the Br comes off as Br minus and an H is removed and comes off with the OH minus as water and leaves something with a double bond. It will leave ethene. The only one that doesn't occur then is A, electrophilic addition. Electrophilic addition happens when something's got a carbon-to-carbon double bond and something like a HBr or a BrBr or a sulfuric acid, a H2SO4, adds across the double bond. With the no double bond in bromoethane, it cannot do that. What's the empirical formula for 4-hydroxypentoene? Well, let's have a look. It's got 5 carbons. So pentoene has got 5 carbons. It's got a double bond between carbons 2 and 3. So at carbon number 2, it's got a double bond, an ene, and it's got an OH group. A hydroxy group is an OH group, carbon number 4. Let's have a look at its structural formula and then we can work it out from there on in. So its structural formula: 1, 2, 3, 4, 5 carbons. A double bond, so instead of CH2 at carbons 2 and 3, we've got CH. That shows there's a double bond in between there to make up 4 bonds on each carbon. We've got an OH at carbon number 1, 2, 3, 4, and there it is. OH in brackets means it's a branch off the chain. So that's the structural formula. If I work out its molecular formula: 1, 2, 3, 4, 5 carbons, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and oxygen. That can't be simplified. I've only got 1 O in there, so I can't divide by another number to simplify the number of O's. So it must be C5H10O is both its molecular and its simplest empirical formula. So your answer is B. Let's look at questions 11 and 12. What's the total number of structural isomers with the molecular formula C2H2BrClF3? So it's got 2 carbons. Each carbon will be joined by a single bond, and then each carbon has got 3 other bonds from it. So the 3 other bonds from each carbon, carbon to carbon, on the first carbon, then you could have any combination of HBrCl and 3 Fs. So we've got HBrCl and 3 Fs. Any 3 of those to go onto the first carbon, and then the remainder to go onto the second carbon. We've got to work through the combinations. So let's have a look at the combinations of that. So I could have all of the 3 Fs on the first carbon on carbon number 3. So carbon number 1. Carbon number 1 could have 3 Fs, and then the H, the Br, and the Cl go into carbon number 2. So if there's not 3 Fs on the first carbon, then there could be 2 Fs on the first carbon, and then that would leave, let's say, if there's 2 Fs on the first carbon, what else could be on the first carbon if there's only 2 Fs? Let's say there's a H, and then everything else, the F, the Br, and the Cl that are remaining, go on the second carbon. The other combination is they have 2 Fs on the first carbon, and instead of an H with those 2 Fs on the first carbon, there's a Br, and then the remaining FH and Cl go onto the second carbon, and then the final combination is 2 Fs onto the first carbon with a Cl this time, and then the remaining atoms, the F, the H, and the Br, go onto the second carbon. Now, because it's completely symmetrical, as soon as I put 1 F onto the first carbon, that's the same as doing each of these combinations here. So you can't put 1 F onto the first carbon because you could label it from either end. Carbon number 1 could be carbon number 2. There's only 2 carbons. So there are 4 different combinations, and your answer is C. Which of the following contains the most chloride ions? This is more complicated than at first it seems. I've got a concentration, 3.4 times 10 to the minus 2, and I've got a volume. I could turn that volume into decimeter cubed by dividing by 1,000. So I could call that 0.0125, 0.03, 0.04 and 0.045. For these, convert these into decimeter cubed, I've got a concentration. And then I can work out each of the number of moles. So moles, concentration equals moles divided by volume. Moles equals concentration multiplied by volume. So if I work out the volume, which I say is 15 divided by 1,000, multiplied by the concentration, now it comes out as 0.00051, and I do that for the remainder. This time 30 centimetres cubed divided by 1,000 multiplied by its concentration, 0.00165, and so forth. 40 divided by 1,000 multiplied by 2.3 times 10 to the minus 2, or 0.023. And then for the final one, 0.045 multiplied by 2.2 times 10 to the minus 2, or 0.022, and I get these numbers. Now, in actual fact, if you'd just gone for these numbers, you would have got it correct anyway as B. But what actually happens is, it's on about the chloride solutions. So if you could write down the number of Cl's in each of these and multiply them up, aluminium chloride, aluminium's in group number 3, it loses 3 electrons and becomes 3+. A chloride iron's in group 7 and gains 1 electron and becomes 1-. So how do you have a 3+ with a 1-? It's because you have 3 chloride ions, 3 1- to balance out the charge on the Al3+. So AlCl3, there are 3 Cl's you need to multiply by 3. Calcium's in group 2, so it forms a 2+ ion. With a chloride ion as a minus ion in group 7, that would be CaCl2. You'd need 2 Cl- to balance out the Ca2+, the 2+ charge on the Cl. So you have to multiply that by 2. Hydrochloric acid is HCl, so that stays the same. That should be multiplied by 1 rather than multiplied by 2. So the number of moles is 0.0092 still. And sodium chloride, sodium's in group 1, NaCl, Na1+ Cl-, so that stays the same as 1. So you'd have to multiply by the number of chloride ions in each of these, 3, 2, 1 and 1 respectively, and the answer still turns out as B anyway. Which is a pair of functional group isomers? Let's just remind ourselves what a functional group isomer is. Functional group isomer is one of the 3 kinds of structural isomers. A structural isomer is where the molecular formula stays the same, number of carbons, hydrogens, oxygens, whatever, but the structural formula changes. So same molecular formula, different structural formula. So structural formula is the way that the atoms are actually joined together. And there's 3 different kinds of structural isomer. Number 1, chain isomer, where you change the length of the chain and introduce branches. Number 2, position isomer, where you change the position of a functional group, a group on the chain, and you change its position maybe from carbon number 1 to carbon number 2, or carbon number 2 to carbon number 3. And then a functional group isomer, where whatever's in there that identifies it, whatever seems to be the group that stands out, called the functional group, whatever makes it what it is and react in the way that it does, is called its functional group, and its functional group changes. So let's have a look here. What defines this? Well, there's a carbon-to-carbon double bond there, and in here there's no carbon-to-carbon double bond. It's lost its carbon-to-carbon double bond, so its functional group has changed. So that is a functional group isomer. Let's have a look at this one. Let's just double check. The OH defines what it is. That's the functional group, and it's on carbon number 1, 2, 3, 4. Here it's on carbon number 1, 2, 3. So the OH hasn't changed, it's just changed where it is, its position. These are positional isomers changing from carbon 4. Looks like 1, 2, 3, 4, 5. Pentan 4-ol going into pentan 3-ol. It's changed its position from carbon number 4 to carbon number 3. That's a position isomer. What's actually changed here? We've got a carboxylic acid here. We've got a carboxylic acid here. 1, 2, 3, 4, 5. 1, 2, 3, 4. I think we've shortened the carbon chain. We've actually not got the same number of carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 in that one. 1, 2, 3, 4. We've only got 4 carbons in this other one. These aren't even isomers because the molecular formula isn't the same. What about these two? 1, 2, 3, 4 carbons. 1, 2, 3, 4. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. So we've got the same number of carbons. In actual fact, what's actually happened here is that the position of the Cl has changed from carbon number 1 to 3, and on here it's changed from carbon number 1, 2, 3, 4. This is a position isomer where the chlorine has changed position from carbon number 3 to carbon number 4. So your answer is A. Let's have a look at questions 14 and 15 then. So the equation for the hydrogenation of ethine, this must be ethine here, and we've got hydrogen, addition of hydrogen is hydrogenation, makes ethane. Experimental yield 65%, so we've made 65% of what we could have made. What's the mass in grams of ethane that can produce from 16.2 grams of hydrogen? So if I've got the molecular formulas of each of these, I can work out the MR of carbons, got a mass of 14, and the hydrogen a mass of 1. So what's the mass in grams of ethane that can produce from 16.2 grams of hydrogen? I've been given a mass, I've got its MR. Why would it give me a mass and an MR? Surely I need to work out number of moles. So moles equals the mass divided by MR. H2, 2 ones, hydrogen having a mass of 1, its MR is 2, so I've got 8.1 moles of hydrogen. 8.1 moles of hydrogen. Why have they given me the equation? The equation is like a recipe really. It tells me the amounts. 1 mole reacting with 2 moles to make 1 mole. So 2 moles of hydrogen makes 1 mole of ethane. We want to work out the mass of ethane. I now know if I've got 2 moles of hydrogen and make 1 mole of ethane, I've got 8.1 moles of hydrogen, so I must make half the amount. I must make 4.05 moles of ethane. I know the number of moles of ethane that I can make in theory. So I should make 4.05 moles of ethane in theory. That's the theoretical yield, but I only make 65%. So 65% of that, 65 divided by 100 multiplied by 4.05, I actually only make 2.63 moles of ethane because I only make 65% of the yield. Now I've got the number of moles of ethane that I actually make. I know it's MR, 2 multiplied by 14 for the carbons, and 6 multiplied by 1 for the hydrogens is 30, and so moles equals mass divided by MR, so mass equals moles multiplied by MR, 2.63 multiplied by 30, 78.98 grams. 78.98 grams is B. The other way of doing it is that you could have actually worked out 4.05, converted that moles into grams, by multiplying 4.05 by 30 and then doing 65% of that would have come out with the same answer. What molecule does not have permanent dipole-dipole? Well, I've got Cl's in there and F's in there. So a C to Cl has got a dipole bond in there. It's got a delta plus and a delta minus because Cl's and F's are electronegative. They're going to have delta minuses and leave a delta plus on the C. So you're going to end up with a polar bond in there, and between molecules polar bonds then create dipole-dipoles. So all of them should have dipole-dipoles, except that if you have a completely symmetrical molecule both along the x and the y axis, if it's completely symmetrical, all the pluses and minuses cancel each other out, and therefore it doesn't have a permanent dipole and it doesn't have dipole to dipole intermolecular bonding. So which one is perfectly symmetrical? C with 4 F's around it is completely symmetrical, so the answer is C. So we'll look at questions 16 and 17. So bromine has 2 isotopes, 79Br and 81Br. The only difference between these 2 isotopes is the number of neutrons. The number of protons, the atomic number or the proton number at the bottom is the same. So they've got the same number of protons and the same number of electrons. The only difference is their mass has changed because the number of neutrons has changed. So the first ionization energy is less than the first ionization energy of 79 is different than 81. Well, no, it's not, because the ionization energy depends on the nuclear attraction of the number of the protons from the nucleus and the number of electrons and shielding and so forth. But the number of protons and electrons are identical in both, so the ionization energy is going to be the same. The atomic radius, again, the atomic radius depends on the number of electrons, the number of electron shells, and the number of protons in there. But they've got the same number of protons, so the nuclear attraction. But the nuclear attraction number of protons and the number of electrons and electrons in shells is identical, so the atomic radius radius is going to be identical. Reactivity depends on the number of electrons in the outer shell, so the reactivity is identical because the number of electrons are the same. The only difference is that the mass spectrum has two different molecular ion peaks. So what that means is, if you take a molecule and you make it plus by removing an electron in a mass spectrometer, and then you measure its mass, then the mass will change depending on whether Br has got a 79 Br with a mass of 79 or 81 Br. So in this sample you could have Br as a 79 or Br as an 81 just naturally occurring, and both would occur, both would be around in nature. And then when you make it a positive ion, a molecular ion, and measure its mass, then you'll find that its mass is different in each case depending on whether the Br is a 79 Br or an 81 Br, so its mass changes between the two molecules depending on what kind of isotope of Br is in there. Which of these is not planar? So planar happens if there's 3 bonds off a carbon. As soon as there's 4 bonds off a carbon, then it becomes tetrahedral in shape. So in other words, which one is not planar, not have 3 bonds, which has 4 bonds? So CH3CO, there's a carbon to hydrogen bond, a carbon to hydrogen bond, and a carbon to double bond oxygen, which counts as 1 bond, 1 species. There's 3 different atoms off that carbon. That one's planar. 3 different H's off that one. Forget about the plus, that's not important. There's 3 different H's off that one carbon. That one's planar. This carbon has 3 H's, no H. It has 4 different groups around it. That's tetrahedral. C2H4 has a carbon-to-carbon double bond, and each carbon then has 2 H's. So it's got 3 different bonds or 3 different groups attached around each carbon. That's planar. This one, CH3OH, methanol, has 4 different groups around the carbon. That's not planar. It's tetrahedral. So look at question 18 and 19. So which of these mechanism arrows is incorrect? So which looks incorrect? A lone pair of electrons with an arrow coming from it is perfectly acceptable. Going to a C, well this is a polar bond with Br more electronegative than the C, so this would have a slight delta plus. That's perfectly acceptable. The Br is electronegative and pulling electrons, withdrawing electrons along the bond towards itself anyway, and is slightly electronegative at delta minus. That breaking and going onto the Br and coming off and breaking and forming a Br minus is perfectly acceptable. So it's either C or D. Lone pair of electrons going to an H, possible, unusual, but it's possible, at least that's correct. I think there's something wrong with C here. It's coming from a bond which is perfectly acceptable, but surely if that bond were going to break, if you've got an N with a plus on it here, an N with a plus on it, then the electrons would go the other way and would go onto the N rather than onto the H to remove the N plus and get rid of the plus by the electrons moving on to the plus. So that arrow, that C, is going the wrong way. It would break and they would move on to the plus to eliminate that N plus, which is unstable. So your answer is arrow C. Next one, how do you work out whether something is Z? So Z is on the same side. What's on the same side? So what you do is you look at this carbon-to-carbon double bond and you trace it back. If there's nothing here, there's an H. So if it's a skeletal formula, if it's got 1, 2, 3 bonds, its 4th bond here is an H. So there's an H there and an H there. So what you do is either side to the left of the double bond, you identify which is the heaviest atom. So going along here, there's a C with a higher atomic number, and along here there's an H with a lower atomic number. So this group here has got a carbon joined to it. This way there's an H joined to it. So this group here would take priority. On this side there's an H, and on this side going along there's a carbon, another carbon, another carbon. So this one would take priority. So along here you've got one on this side and then one going up on the other side. That is an E isomer. So that's not correct. B, let's have a look. To the carbon-to-carbon double bond. From here I've got a C. That way I've got a C, so both of them have got the same atomic number, but this has got H's attached to it. This has got another C with another C with another C. So this one takes priority because as you trace further along the chain, then you've got carbons with higher atomic numbers. This one takes priority over the methyl group, and on this side you've got an H coming down here with a lower atomic number. This way you've got a carbon with a higher atomic number. This one takes priority. So you've got one coming down and one going up. This one is an E isomer. What about this one here? So this way I've got a carbon and a carbon here, but this carbon here is a methyl group with just H's on it. This one has got a carbon joined to another carbon, joined to another carbon, joined to another carbon. So as you go further on the chain, these carbons have got higher atomic numbers. So this one takes priority. This way you've got nothing coming off here, shown at least. So you've got an H coming off here to give the fourth bond. And this way you've got a carbon with a higher atomic number. These here, C has got a carbon here. This group takes a higher priority than just this carbon because this carbon has got lots of other carbons going along a higher atomic number. This one takes priority, and on this side this group takes priority over the H. The C is on these two on the same side going down and down, so this one is a Z isomer. Let's just check this one as well. This one here to the left you've got a carbon. This way you've got a carbon, both with the same atomic number, but as you go along further on the chain, that one's got another carbon with higher atomic number than the H's that are joined to this carbon. So this one takes priority, that one's going up, and then down this way I've got an H, and coming down I've got a carbon with a higher atomic number. This one's coming down. So that one's got this one taking priority going up, and this one taking priority coming down. They are opposite. That is E. So your answer is C. C is your Z isomer with the groups with the highest priority, both going down from that carbon to carbon double bond. Question 20. Let's have a look what's happening. We're having a reaction between magnesium and sulfuric acid. Magnesium is a reactive metal in group 2. Sulfuric acid, a metal and an acid will make hydrogen. So they're monitoring the volume of hydrogen that's made. It goes up quite quickly and then stops being made. The reason it stops being made is because one of the chemicals has run out. Which one's run out? Well, there's an excess of magnesium, more magnesium than we need. So the sulfuric acid is what's run out. So the sulfuric acid has run out at this point here, and no more hydrogen has been produced. What happens when you use half as much sulfuric acid? Well, the sulfuric acid runs out, and so I've got half as much sulfuric acid. I've only got half as much product, half as much hydrogen being produced. So the volume of hydrogen here will be halved and will eventually come down to here. So I've got half as much hydrogen. I've got either answer A or answer D, where the volume of hydrogen produced is only half what it is in the first graph. Now then, if I'm using half the concentration, what happens if I reduce the concentration? Well, reducing the concentration means that the particles are further apart. So the particles are further apart and you get fewer successful collisions. So it's going to go more slowly. So the line is shallower because it's making the hydrogen more slowly. It doesn't rise and produce at the same rate as in D and the first graph. I'm making it the same rate. It's answer A because it would make half as much hydrogen because the sulfuric acid has half as much and therefore will run out and make half as much hydrogen. It also make it more slowly because the particles are are spread out further apart and so fewer successful collisions. Answer A. Question 21. The maximum uncertainty when weighing 0.250 grams on a balance was 0.001. In other words, it can be 0.001 grams out. That's what the balance's accuracy is. It can be 0.001 grams out. So that's how far out it can be, and you're weighing out 0.250. So you take 0.001, that's how far out it can be, divided by the mass that you're actually measuring, multiplied by 100%, and that'll give you the percentage uncertainty. 0.4% B. Which species has the same number of electrons as CH3 with a dot? So what you have to respect is that dot is an electron that's still there on the carbon. It was an electron that was once a bond, but it's still there. So how many electrons does carbon have? Well, carbon has an atomic number of 6, a proton number of 6. It has 6 electrons, and that's one of its 6 electrons. It was once in a bond, but it's got it back. So that's got 6, and the hydrogens have got 1 electron each, 7, 8, 9. So in there, there's 6 on the carbon, and there's 1 from each of the 3 hydrogens, because a hydrogen has got 1 electron. 6 on the carbon, because carbon's got an atomic number of 6, and that 1 is part of those 6, that 1 unbonded electron there, and 3 from the hydrogens makes 9. Now we need to check what the others have got. Which other ones have got 6 plus 1 plus 1? I've got 9 electrons in there. Well, CH2 has got 6 from the carbon and 1 from each of the hydrogens. That's 8. 6 from the carbon, 3 from each of the hydrogens is 9, and a plus means that it's lost an electron somewhere. So that has got 6, 7, 8, 9. Take away 1 for 1 being lost. That has 8 as well. CH3 minus 6, 7, 8, 9, 6 from the carbon, 1 from each of the hydrogens is 9. A minus means it's gained 1, so that has actually got 10. What's D got? 6 from the carbon, 1 from each of the 4 hydrogens is 10, and it's got a plus, which means it's lost an electron, it's got 9. So your answer is D. D has got the same number of electrons as CH3 radical. Which of these could be a carboxylic acid? So a carboxylic acid has got a C double bond O in it, around about absorption 1700, something like that, around about here. So it's looking like either A or D, because this one hasn't got one, this one hasn't got one, D's got one here, A's got one here, so it could be A or D. And then a carboxylic acid has got an OH group, which is going to have a broad absorption around about 2,500 to 3,000, something like that. So your answer is A.